All right, we solved exponential and logs last class, and we're going to continue to solve some today. First, we're going to start with a little cheat. You can use the calculator to assist you in solving by entering the equations into y1 and y2. The steps are listed right here. But basically, we take one side of the equation and put it into y1 and the other into y2. So I would plug in 7 natural log of 4x into the y1 and 16 into the y2, like I've done here. You have to be able to see the intersection in the calculator. So when you hit graph, you want to be able to see the intersection. In this case, I don't see the intersection. The standard window is -10 to 10 and -10 to 10. If you think about 16, y equals 16 is a horizontal line at 16. So of course I don't see it, it's way up here. So I do have to open up my window to verify that it is there. So I want to make something bigger than 16. I'll go ahead and do 20. Now I can see my log and I can see my horizontal line at 16. This point of intersection is our solution. So we hit second, trace, intersect, enter, enter, enter. And there it is at 2.458. Remember, we do keep three decimals. So we would say x is approximately 2.458. And there is our solution. Obviously, you didn't do any math to get that solution. The calculator did all the work for you. So this is a great way to check your work. If it says do it algebraically, you would not want to do this because that is not algebraically, but it is a great way to check your work and allows you to do some problems that are a little bit harder that way. All right, we're going to move on to some models of exponentials that you need to be able to do. It says here that an exponential growth or decay model is when we use an equation like this, a equals p times 1 plus or minus r to the t power. It models an exponential growth or decay. If it is growing, we use the plus. If it is decaying, we use the minus. P is the initial amount, R is the rate of growth or decay, and T is the time in years. You use this in Algebra 2, so this should be a refresher. We're going to look at some problems where we would use this equation. It says the rate in the number of reported cases of robberies is dropping at about 7% per year in a given region of the country. The number of cases reported this year was about 156,000. If the number continues to drop at this rate, what will be the predicted number of cases 2.5 years from now? When you are working these problems, one of the things that you want to make sure you're looking for is keywords like dropping, depreciation, appreciation. That's what's going to help you determine whether it's exponential growth or exponential decay. Dropping means it's going down, so this would be exponential decay. So we would want to use this model with the minus. To look like that. The other thing you got to be careful with is the percentages. When we use this in the formula, we need to just change it to a number. To change a percent to a number, you move the decimal over 2 places. So 7% becomes 0.07. Now we're ready to set this up. It tells us that it was 156,000 cases. So that's going to be our principal or our initial amount. It is doing 1 minus 0.07 because we said it is decaying and the percentage is 7%. And we want to know how many cases there will be in 2.5 years. So 2.5 is going to be the time. This is going to be the easiest type of question they give you because it's just plug it in the calculator since our missing variables on the other side of the equal sign. So we're going to put this in the calculator. 156,000, and you can't put this exactly the way you see it. 1 minus 0.07 raised to the 2.5 power. That's 130,116.38. Now, in this case, we're talking about the number of cases of robbery. You can't really a third rob someone, so you would want a whole number for this. We do take truncate or round, either one. So the amount is going to be approximately 130,116 cases. If it's something like this where it's cases, people, animals, you want to keep it to a whole number. If it's money, you want to do 2 decimals because that's how we do money. So keep those things in mind as you write answers. All right, on this next one says, suppose you purchased a car in 2018 for $26,000. If the value of the car decreases at 16% each year, how much will your car be worth in 2020 and 2024? This is very similar to that one. We start with 26,000. It is depreciating, so it's going down, decreases by 16%. So that would be 0.16 in this place. And from 2018 to 2020 would be 2 years. We would have the same equation for 2024, but it would be 6 years. That would be the difference between those 2 equations. And then again, you would put them in the calculator. So we type in 26,000, 1 minus 0.16 raised to the second power. You can use your calculator, copy and paste when you're taking test or quizzes and you need to repeat something like that. So we arrow up to where we have the initial equation, and then we just change the 2 to a 6. And so there's our 2 values. These are both money, so I would want to keep 2 decimals. All right, so there's the value of our car after 2 years and after 6 years. Number 6 says a home in Frisco is currently worth $300,000. If homes in Frisco are appreciating at a rate of 4.7% per year, when will the home be worth $350,000? So again, we're looking for those keywords. Appreciating means going up in value. This is true in real life. Cars go down in value, houses go up in value. So you want to keep that in mind when you're doing your investments. So we're going to set this up here with our initial amount of $300,000. It is going up, so we're going to do 1 plus 0.047. Notice what I did there with that decimal. I moved the decimal over 2 places, so that's 0.047. A lot of students mess that one up because that 4.7 kind of tricks them. You still want to move the decimal over 2 places to change it to a decimal. We don't know the amount of time here, so t is actually my variable in this one. In the amount, I want what I'm looking for, which is 350,000. This is the type of problem that's going to be a little bit harder because now the variable is not on the other side of the equal sign. It's up here in the exponent. So we're going to have to solve this the way we did in last class's solving equations. So my first step is to divide by 300,000. And some of these numbers aren't great, so you're going to have to use the calculator to do some of those. Yes, this will be on the calculator portion of the test. And so we get 1.167 is equal to 1.047 to the t power. Now, I rounded because I wanted to write the step here on my paper, but remember, you're not going to round until the very end of the equation because that can change your numbers quite a bit. So at this point, I need to free this t out of the exponent. That means I'm going to have to use that definition to change this to a log so that I can free it out of the exponent. Anytime that the variable's in the exponent, you're going to have to use that definition to free it out of there. So we drop the base. So we get a log with a base of 1.047. The 1.16 becomes my argument and the t is freed. So when I put this in the calculator, I'm going to do alpha window to get to my log base. In the base, I'm going to put in my 1.047. That was the part that was inside the parentheses. then in the place of my argument, I want to put all of this. I don't want to round. So I use my arrow key to highlight that and hit enter. And then it puts the entire thing in there. That way I'm not rounding until the very end. And so there's our answer of 3.35628, so on. And with time, it is continuous. So you can use a decimal for this one. So I would say time is approximately 3.4 years. You can use a decimal because time is continuous. Same thing with money. You can use a decimal for money because we can use 2 decimals to show the cents. All right. Now we're going to look at compound interest formula. The growth in the value of investments or earning compound interest is modeled by an exponential function. The total amount of an investment, A, earning compound interest, is right here. The difference in this formula, because the P is still principal, R is still the rate, but we're dividing that R by N here, and then we have an N being multiplied times the time there. That N is the number of times compounded per year. That means how many times are we going to stop and add the interest basically to it? Credit cards do this. You have a balance at the end of the month, they stop, figure out how much interest. And then if you don't pay any of it off, then the following month, that's going to be your new balance with that interest. They're going to start the process all over again. So they compound 12 times a year. Anything that you finance really is going to do this. How many times is it going to compound a year? That's what's determined here. That's what that N value is. In some cases, they will compound continuously. So when it says compounded continuously, then we're going to use this natural formula right here, E to the RT. So instead of finding the rate this way, it's going to be this E. That's the natural compounding form. All right, so we're going to look at what that does here with an investment. It says find the amount of $500 investment after 8 years at 6% interest compounded, and here's the different ways. So the only thing that changes in the formula, so we've got 500 is our principal, 1 plus 0.08, because that's the, that was the years, 0.06 was the interest. And then the time is 8 years. The only thing that changes in this formula is going to be the N value. So these 3 right here are going to be the same thing with different N values. Annually happens 1 time a year. So the N would be 1. Quarterly happens 4 times a year. So the N would be 4. And monthly happens 12 times a year because there's 12 months in a year. So the N would be 12. So this formula would be the 1 plus 0.06 over 12 and 12 times 8 in the exponent. And then here we've got 500 and then 4 times 8 in the exponent. And this is one that I told you that on test, you're going to use that copy and paste because you don't want to sit there and waste that kind of time. So we hit 500 first, and then alpha window gives us that log base. What am I saying? 500, and then we're going to do 1 plus alpha y equals gives me the numerator over denominator. 0.06 is the rate, 1 is the N, raised to the 1 times 8. Now, if you think about that 1, that just takes you back to the simple formula, which was on the other side. So annually is really that simple interest that we saw on the other side. That gives us $796.92. Now, here's where I tell you, you don't want to waste time and retype all of that in there. So you can use your arrow key to highlight that. Hit enter. And then the only thing we want to change is that N. So I would do 12 in the place of the N there. And in that case, it went to $807.07. So the more you compound, the more you're going to end up with, because again, you're earning interest on that interest. And then I would do it again for the quarterly one. And in this case, we want 4. And we had $805.16 in that one. So I'll go ahead and write those amounts here. All right, to our next one, the one that says continuously. And only when it says continuously do we use the Pert equation. That's what we usually call this one, is Pert. That's when we do our principal times e raised to the RT. We haven't talked about e yet. Remember, we said a log with a base of e was the natural log. E is a number. E is 2.718281828 and so on. Remember, it's the pi of algebra 2. So that's the one that we're going to use there. So we get our amount is equal to 500 e, which is a number, raised to the 0.06, which is the rate, times time, which is the 8 years. When you put this in the calculator, let me clear my screen here. We're going to hit 500, and then we want the e. And so you've got 2 choices. There's one right above the division, and then the one that has e and automatically raises it to a power is the one right over the natural log. So you hit second natural log, and it will type the e ready to go into the power there. So 0.06 times 8. That's how we do the continuous. And so that would be 808.04. And so that's going to give us the most, because the more you compound, the more you're going to make. They do get closer and closer together as you start compounding more. So the biggest change you'll see is from here to here. But these are a little bit closer together as you start compounding closer. That's why it ends up being that natural E. All right. You have deposited $1,000 in an account that pays 6.25% interest compounded continuously. How long will it take your money to triple? So triple 1,000 would be 3,000. So here's the amount we want it to be. Here's our initial amount. Since it says compounded continuously, I know I'm using E as that growth factor. My percentage is 0.0625 because I moved that decimal over 2 places. And what we're looking for is the time. So this is one of those that you're going to have to solve for because our variable's in the exponent. So I divide by 1,000. And we get 3 equals e to the 0.0625 t. To free this out of the exponent, that's the only way we can solve this, is to get that t out of the exponent. In order to do that, we are going to change it to a log. So we use the definition to change it to a log. We drop our base, and so a log with a base of e is a natural log. And then we switch, so 3 is equal to 0.0625 t. I've run out of room over there, so I'm going to go over here. So now I divide by 0.0625. And so t is approximately, to put that in the calculator, we hit the natural log, which is that ln button to the left of 4. That's our natural log of 3. I make sure I close my parentheses because that's where the argument is going to end. And then I divide by 0.0625. And so t would be 17.6 years. All right, we've got a couple more to set up and solve here. It says if you invest $5,000 at 7% annual interest compounded monthly, how long will it take to double your money? So double 5,000 is 10,000. We want compounded monthly, so we're going to use the one that's 1 plus 0.07 over 12 and 12 to the t power. My first step is to divide by 5,000. And so we get 2 is equal to, and you can go ahead and simplify that inside part. Now, it's time to change that to a log. The only way you can get this out of the exponent is to use that definition to change it to a log. So we get a log with a base of 1.0058. 2 is equal to 12t. So I have freed this out of the exponent by changing it to a log. My last step would be to divide by 12. And I do want to practice putting this in the calculator with you because, again, I don't want you to make a mistake on the way you put that in. So here we go. Alpha window allows me to do the log base. For the base, I want this part right here that I had before this. So I'm going to go ahead and highlight it. And put that into our base. And then 2 is my argument. I get out of the argument. So I make sure I'm outside of that parentheses and then divided by the 12. And so that is 9.9 years. All right. The number of bacteria in a colony is growing continuously. The amount at the beginning was 4,500. The bacteria are growing at a rate of 5.5%. Predict the number of bacteria. All right, this one gets a little bit tricky because people think continuously here to use PERT, but it does not say compounded continuously. It just says it's growing continuously. You can't really compound bacteria, so that doesn't work. So here we would have 4,500 as our initial amount. It is growing, so it's going to be 1 plus, and our rate is 0.055. I move this decimal over 2 places. It wants us to predict the number of bacteria after 4 days. So 4 is going to be my time. And so now we're ready to plug this in the calculator and verify how many bacteria we have. So we're going to have 5,575 bacteria in the colony. Notice that I did not leave any decimals because we can't have a partial bacteria.